At first glance, Arrow Lake might seem like any other CPU. But when we look at the silicon below the heat spreader, it becomes immediately obvious that Arrow Lake is different. The Core Ultra 9 285K you are looking at right now combines 7 different chips into a single package. 4 active and 2 structural dies are sitting on top of a massive 2.5D silicon interposer, interconnected by Intel's Foveros technology. Thanks to the amazing work from Fritz, and for the first time exclusive in this video, we will show ultra high resolution die shots that reveal Arrow Lake in mesmerizing detail. In this video, we will analyze every square millimeter of Arrow Lake, including a detailed look at Intel's new Cove CPU cores. Without spoiling anything, there are quite a few surprises hidden inside the silicon. I've put chapters in the video timeline below so you can jump to the parts that interest you the most. Without further ado, let's go on a deep dive into the silicon heart of Intel's Arrow Lake. Arrow Lake is Intel's first tile-based desktop CPU. Intel calls chiplets tiles, and they actually do look a bit like tiles you'd find in a kitchen, for example. Each tile has a different function, and combined they work as one single CPU. The tiles are physically very close to each other, very different to AMD's approach with more distance between chiplets. Starting on the right side of the chip, we can find the GPU tile. As the name implies, it contains the Alchemist iGPU. This tile is manufactured in TSMC's N5P process. At only 23 square millimeters, it's also the smallest active tile on the package. To the left of the GPU tile is the SoC Tile. The SoC Tile houses important areas such as the memory system, display and media engines. It also acts as a central interconnect hub for all adjacent tiles. It's produced in TSMC's N6 node and comes in at 86.6 square millimeters. Another tile that's based on the N6 process is the I/O tile. As the name implies, the I/O tile houses input and output logic such as PCI Express and Thunderbolt. At around 24.5 square millimeters, it's only slightly larger than the GPU tile. The heart of Arrow Lake, and also the largest tile at over 117 square millimeters, is the compute tile. It contains the CPU cores and the L3 cache. It's produced in TSMC's N3B. The remaining 2 dies that are visible on the top layer are for structural support. There's a tiny 2.5 square millimeter one in the top right above the GPU tile, and a larger 17.5 square millimeter one on the bottom left. They make sure that there's a more or less coherent surface and no large gaps. Last but certainly not least, there's the silicon interposer. It sits below all the top tiles and covers the entire area of the chip. At almost 303 square millimeters, it's by far the largest piece of silicon on Arrow Lake. The interposer is manufactured in Intel's 22FFL process node, internally called P1227.1B. The interposer doesn't contain any active transistors and is used for the Foveros die-to-die interconnects. Now that we know the layout of Arrow Lake and the functions of each tile, let's start our silicon analysis with the GPU tile. Arrow Lake S uses Intel's Alchemist architecture with 4 Xe cores. A Xe core is similar to what a shader engine is for AMD or a GPC for NVIDIA. Aside from the 4 Xe cores, the GPU tile should also contain 4 MB of shared L2 cache, and of course every GPU needs central control logic. Plus, since the GPU is its own tile, there has to be an area reserved for the die-to-die interconnect. Let's see what we can find. The L2 cache is easy to spot if we look for repeating patterns of SRAM cells. The 4 MB are split up into 4 small clusters with 1 MB each. If we zoom in, these clusters are further divided into 2 parts of 512 KB with the L2 cache tags sitting in between. But we can go even deeper. The smallest function blocks are tiny 16 KB cache blocks. I wasn't joking when I said ultra high resolution die shots. Fritz is just on a different level. Interestingly, there's another visible block of SRAM cells which isn't part of the L2 cache. I'm pretty sure it's a cache since there seems to be tags nearby, but I don't know the exact function. I'll label it mystery cache. If you have an idea what it is, please leave a comment down below. Staying in the center of the GPU tile, we can spot the Foveros die-to-die interconnects. They show up as 2 rows of alternating contacts and look a bit like PCI Express pins on a GPU. Both rows are so far apart that some of the L2 cache blocks are located in between them. It does look very space efficient. When we analyze the SoC tile later, we will look for matching interconnects. Next, let's locate the 4 Xe cores. They are split up with 2 above and 2 below the center area. Zooming in, we can see that a Xe core has an almost square middle part and repeating blocks left and right. These are the vector engines, XVE for short. They are organized in pairs with each block containing 2 vector engines. If you watched my Navi 48 video, you know that AMD does something similar. They also combine 2 compute units into one function block, called workgroup or simply dual compute unit. This seems to be the most efficient way because you can share resources between units. With 8 dual XVEs, a single XE core contains 16 vector engines. And since the GPU tile has 4 XE cores, there is a total of 64 vector engines, which means we can confirm Intel's claim. Arrow Lake S indeed has 64 vector engines. Seeing is believing. The center area of each XE core contains 192 kilobytes of L1 cache, load and store functions, a ray tracing unit, and other control and threading functionality. Zooming out again, the unmarked areas in the center of the GPU tile is used for central command and control, and interconnects that allow the data to flow between the 2 XE cores on top and bottom. Intel generally calls it render slice. We can also see the layout of the GPU tile. It is exactly as wide as a single XE core, which is a very cool design decision. The GPU tile is so elongated because Intel just stacked the XE cores on top of each other and used spaces in between for the L2 cache and central render slice. At 23 square millimeters, the GPU tile is actually the smallest active tile on Arrow Lake, but it allows Intel to integrate a capable GPU on a modern 5nm node. The only downside is that we aren't getting the latest XE2 architecture as seen on Lunar Lake, which, to be honest, isn't a big deal for a desktop CPU that most likely will be paired with a dedicated GPU. Next up is the SoC tile. This one is interesting because not only does it contain some of the most important functions of the chip, such as the memory system, it also acts as a central interconnect hub and is the only tile that is connected to all the other tiles. Starting at the top, we can locate the DDR5 memory physical layer. If you count the individual PHYs, there are 18 of them, 16 for the dual channel DDR5 and another 2 for ECC functionality. Not every PHY is located directly at the shorelines of the chip, which makes the pinout a bit more complex. But because there's a silicon interposer, it shouldn't have any negative impacts on signal stability. Below the memory PHYs, we can locate the memory controllers. It looks like there are 2 of them. The area next to the memory controllers and below the memory PHYs is the neural processing unit, or NPU for short. On Arrow Lake S, Intel is using a 3rd gen NPU with 2 visible MAC arrays, 4 MB of shared scratchpad RAM, and 4 Shave digital signal processors. And while this NPU implementation might not be the most powerful, it comes in handy when you're using effects such as a background blur in a video call, because running these basic AI workloads on an NPU means you don't need to use your CPU or GPU, which saves power. A bit to the right, just at the border of the tile, we can find 8 lanes of what looks like PCI Express 4.0 PHYs. I'm pretty sure these are in fact the DMI 4.0, which is used to connect the CPU with the chipset on the motherboard. Arrow Lake has a pretty powerful media engine that accelerates video DNN coding, including new codecs like AV1 at up to 120 FPS 10-bit 8K HDR. This capability doesn't come for free though. The media engine takes up a massive area. And there's something strange going on because the function block is interrupted on the right side close to the GPU tile. If we look closer, the interruption is one of the 2 Foveros rows that enable the die-to-die interconnect with the GPU tile. It's interesting how Intel designed these interconnects because they're very tightly integrated with the function blocks around them. We can see the same on the bottom left where the display engine is located. Just as with the media engine, the die-to-die interconnect towards the I/O tile is neatly placed in between the display engine. Right next to the display engine, we can also find the display PHYs for the display output and some additional USB PHYs. Arrow Lake does support PCI Express 5.0 and we can locate 16 Gen 5 lanes on the bottom right of the SoC tile. 12 PHYs are directly at the edge of the chip, but just like with the memory PHYs, Intel is stacking 4 more in second row. Placing I/O away from the shoreline of the chip isn't impossible, it's just not ideal. But again, the silicon interposer allows Intel to be more flexible with the placement of interconnects. The area next to the PHYs with visible SRAM cells is used for the PCI Express buffers. With that, we have marked most of the area inside the SoC tile. Most, but not all. The die-to-die interconnect for the compute tile is located to the left of the memory controllers. But what about the rest? First of all, without help from Intel's engineers, it's impossible to label every single part of such a complex chip. And then there's the interconnect functionality. The SoC tile contains a data fabric that allows the adjacent tiles to talk to each other. The iGPU has to access the display PHYs, compute tile has to talk to the memory controller, and so on. much of the unlabeled areas are the data path that Intel calls scalable fabric. The SoC tile is like an autobahn for data. Before we tackle the compute tile, let's take a quick look at the I/O tile, which is a kind of extension to the SoC tile. Right at the border, we can see the Foveros die-to-die interconnects. The bluish area next to it looks exactly like the display PHYs on the SoC tile, and we can be pretty sure that this is indeed another display output. But it's not a standalone display PHY. This one enables the display over Thunderbolt functionality, because right next to it we can locate 4 Thunderbolt 4 PHYs with a pretty massive dedicated control and buffer area above. Aside from Thunderbolt, the I/O tile contains PCI Express logic with 8 PCI Express 4.0 PHYs and an additional 8 PCI Express 5.0 PHYs, plus the required buffers. The idea behind the I/O tile is that it's scalable. Intel can design smaller and larger I/O tiles depending on what interconnect options they want to offer. You could also release a CPU without an I/O tile, because the SoC tile has its own I/O. In total, Arrow Lake S has 24 PCI Express 5.0 lanes, 16 on the SoC tile and another 8 on the I/O tile. But as far as I know, only 20 of them are available, for reasons I don't know. With 3 out of 4 active tiles analyzed, there's only one left, the compute tile. I think it's safe to say that it's the most important one, especially when you think of Arrow Lake as a CPU. The compute tile is home to 8 Lion Cove P cores and 16 Skymont E cores, plus 36 MB of shared L3 cache and a ring bus that connects all cores. The L3 cache is easy to spot. We just have to follow the large clusters of SRAM in the center of the tile. There are 12 L3 cache blocks, each containing 3 MB. And since 12 times 3 is 36, we once again can confirm Intel's claims. It's interesting to note that 10 of these cache blocks are using the same layout, and then there are 2 on the very right which use a different layout, but they still hold the same amount of SRAM cells. I'm sure this different implementation did cost a few Intel engineers a lot of time. In the center between the L3 cache blocks, we can locate the L3 cache tags and the ring agent. Each core needs a ring bus stop to access the L3 cache and communicate with the other cores on the compute tile. To complete the ring bus, 2 Foveros die-to-die interconnects are located at the very right edge of the tile, facing the matching interconnects on the SoC tile. When it comes to the CPU core layout, Arrow Lake is introducing a pretty big change. Previously, Intel always placed P and E cores in groups, all P cores right next to each other, and then the E cores. Arrow Lake changes that. As you can see, the 4 Skymont E core clusters and the 8 Lion Cove P cores are spaced out over the compute tile. The most likely reason for this change is thermal density. Clustering all P cores together means that under heavy load, almost all thermal energy is generated in a limited area, which is prone to cause heat spots. By mixing P and E cores, the thermal load is spread across the entire compute tile, which should result in better heat dissipation and reduced hotspot temperatures. A good move from Intel in my opinion. If we zoom in, we can see that each E-core cluster contains 4 Skymont CPU cores and a total of 4 MB shared L2 cache. The cache is split up into 2 parts with 1.5 MB and 1 part with 1 MB. Plus, there's area used for interconnect and control functions. By the way, if you're still watching, leave a comment down below. I'd like to know how many of you stay for the whole video. Even more interesting is the P-core layout. Not only did Lion Cove see massive architectural changes, the switch to TSMC's N3B process node also drastically altered how Lion Cove looks like compared to previous Intel generations. Let's zoom in and take a closer look. The clock driver for each core is located in the bottom right. It's likely that there's other functionality in this area too. For example, interconnects to the L3 cache, or a ring stop, or other logic. But even with ultra high-res pictures like these, it's hard to be more specific. What is very easy to tell though is the private L2 cache area. If we count the visible SRAM cache rows, there's 1.5 MB in the block on the left and 1.5 MB plus an additional 256 KB for ECC functionality in the block on the right. Lion Cove on Arrow Lake has a massive 3 MB L2 cache. That's 3 times the size of the L2 cache on Zen 5. We can also spot the dedicated L2 cache tags and the central cache control area. One interesting point is that the extra cache bits needed for ECC are usually already included in the SRAM cell design, but on Arrow Lake, Intel had to add more SRAM cells to accommodate ECC, which means ECC isn't already part of the SRAM cells. This might be because TSMC didn't offer the right standard cells for the short-lived N3B node. It threw me off in the beginning because I always counted more than 3 MB of L2 cache. Thanks to Nemes, who helped me solve the riddle. Next is the new L1 cache, which is actually more of an in-between cache. Intel should have called it L1.5 in my opinion. It's pretty large at 192 kilobytes, much larger than the L1 cache on previous architectures, which is now called L0 cache. The real L1 cache, now called L0 data cache, is located inside the load store area of the CPU core and holds up to 48 kilobytes of data. The L0 instruction cache sits inside the decode area, and even though it's using a much smaller area, it can hold 64 kilobytes of instructions. The size difference is because instructions come in more predefined values, which means you can optimize the instruction cache for size, while a data cache has to be ready for more uncertainty. The small area in between is the translation look-aside buffer, or TLB for short, which maps or translates the virtual to the physical memory. Continuing, the branch prediction area is located in the top right of the CPU core. That's where the cores try to predict where the instruction will go in the execution pipeline. If the guess is correct, it can result in a major speedup. After the branch prediction, the data flows into the out-of-order scheduling. Here, the CPU orders the incoming instructions so that they can be executed in the most efficient way possible. Once the order is decided, the instructions are dispatched to either the floating point or the integer unit. It's interesting to see how much larger the FPU is compared to the integer execution, and the die shots from Fritz is high-res enough to see the individual floating point and integer registers too. The unlabeled area in the center should be related to memory tables and mappings and could also include data paths within the CPU cores. With that, we've mapped the entire Lion Cove P-core. It's a very dense design, and while it does retain some of the layout from previous Intel CPU cores, the visible changes are massive. But all I do is look at silicon. If you are interested in a detailed architectural analysis of Intel's Lion Cove CPU cores, I highly recommend Chips and Cheese. They made some amazing block diagrams which helped locating the individual areas inside the CPU cores. Also, another big thank you to Nemes, who was a great help figuring out many of the details. Now that we've analyzed all the tiles located on top of the interposer, let's talk about the interposer itself, because without it, the entire chip wouldn't be possible. The base tile is what enables Intel's disaggregated tile-based design in the first place. It's also the only chip on Arrow Lake manufactured by Intel Foundry, though we have to remember that the entire packaging is also done by Intel using in-house technology. I've talked about Foveros before, and it can be a bit confusing because Intel combines different technologies under a single name. The version of Foveros used for Arrow Lake is called Foveros Omni, and it's using tiny microbumps to connect the top tiles with the interposer below. These microbumps are still solder-based. Arrow Lake is not using hybrid bonding, but it's a much more advanced interconnect technology compared to AMD's Infinity Fabric on package. The interconnects between each tile are routed through the interposer. That means they go down through the microbumps into the base tile. And then they are reconnecting upwards, again by means of microbump, into the adjacent tile. The result is a very short physical distance that enables low latency and a lot of bandwidth while still being power efficient. If we look at just the Foveros die-to-die areas, we can clearly see where these interconnects are located. Because the tiles on top of the interposer also need power and data connections, TSVs are used to connect them directly through the interposer. If you are interested in how Foveros works in detail, I can recommend my Meteor Lake deep dive. It's an older video, but the technology works the same. To say that Arrow Lake is an interesting design would be an understatement. Right now, it's the most complex consumer CPU you can buy. The sheer amount of engineering that went into this chip is insane. Intel stayed monolithic for a very long time, but with Arrow Lake, they not only embraced the chiplet era, they went all out. It's a bit sad that the public opinion of Arrow Lake seems so negative. Looking at current reviews, it offers the same gaming performance as Raptor Lake and much stronger application performance, while using considerably less power. In my eyes, it's an obvious improvement over Intel's previous offerings. And I'm not only saying that because of the amazing silicon that's inside. Intel's tile-based design is the building block for its future architectures. And with Panther Lake as a Lunar Lake successor, we should be seeing the next step later this year. As always, Fritz will release the die shots you saw in this video on his Flickr page, so you can download them in their full glory. I put a link in the video description once they are available. And there's one more surprise. Arrow Lake isn't the only chip we got ultra high-res die shots of. There's also a complete set of Lunar Lake pictures, which should be released alongside Arrow Lake. I've also done a full silicon analysis that's available on my Patreon. And if I find the time, I'll do a Lunar Lake video at some point in the future. I hope you enjoyed this video and see you in the next one.